welcome back. Now we talked about the statically admissible stress fields. What were they? They are stresses that satisfy, so let us go here, equations of equilibrium over all the inside parts, and they have to satisfy traction boundary conditions wherever we know the traction. Basically, if you already know the traction or the stress, it has to meet that. Wherever we don't know the traction or stress, it has to meet equations of equilibrium. That's the idea. And we looked at a particular example, which was for a beam hanging on its own weight, and we found out that sigma zz equal to rho g times z is a statically admissible stress field. Now next thing will be called a kinematically admissible displacement. So what's a kinematically admissible displacement? That's actually extremely easy. Any differentiable displacement that satisfies the displacement field, the displacement DCs on d omega 2. What I mean that, if you remember, you come back to the continuum potato, all that the kinematically admissible field has to do is to satisfy this. We don't care about anything else. That's all. That's all it has to do. So let's look at an example. You can see it's much simpler than the statically admissible stress fields. Look at an example, or same hanging beam problem. All it has to do is to satisfy u equal to 0 here. So let us say that the beam is of length L. We don't care about what happens to u in any of these places, because this is the only one d omega 4. This is all d omega, this is the only one that's d omega 2. This is all d omega 4. Nothing happens there. We don't care about it at all. We'll worry about the stresses, have to deal with that. All I have to do is to make sure that it meets this condition. For example, I can put ux equal to 0, uy equal to 0, uz equals a times L minus z. So L is that, A is some constant. You can see at z equal to L, because I'm going to measure my z axis from here, right? At z equal to L, you get uz equal to 0, ux equal to 0, uy equal to 0. So it meets that. That's all. Hey, you can say, what about uz equal to a times L minus z cubed? Yeah, that will also meet. uz equal to a sine L minus z. Sure, that will meet. All of them are kinematically admissible. And of course, I have to specify all of them, not just one of them. ux equal to 0, uy equal to 0, uz. You can see that the requirements for a kinematically admissible displacement field are much smaller than the requirements for statically admissible stress fields. Okay, so that's item 1. Now we come to the fact, hey, wait a minute, there are many different strain fields, displacement fields that all satisfy the equations of equilibrium. That all satisfy the boundary conditions. So which one is the correct one? So now we come to the statement of the problem. Find sigma and u such that A, sigma ij comma j plus bi equal to 0 inside omega b. Epsilon ij equals to ui comma j plus uj comma I divided by 2 must be equal to sij kl sigma kl. This is Hookean material. Oh, by the way, and then sigma ij equal to sigma ji. C. Sigma ij nj equal to ti on to omega 1 equal to 0 on to omega 4 and ui equal to ui star on partial omega 2. So it has to sort. So if your stresses and displacements satisfy all of them, you have found a solution to the problem. Once you know the displacements, you can calculate the strains. That's why we needed the differentiability. So a statically admissible stress field satisfies only A and C. Let us call this C1 and C2. So statically admissible stress field satisfies A and C1. Kinematically admissible strain displacements satisfy only C2. The missing link is the Hookean assumption. Once you add that, the statically admissible stress fields and kinematically admissible displacements have to be linked. So this is the link. And now what will happen is, not all statically admissible and kinematically admissible situations will meet this link. So it becomes the link which is the problem. This is called the boundary value problem of elasticity. This thing. So once you convert it into this problem, you can use the tools of mathematics. Converting it into this problem is your task. Using the tools of mathematics, I will show you how to do, but converting it into this problem is your task. Thank you.